It's a great pleasure to have you here, Jonathan, and congratulations for your assistant professorship that you're gonna start immediately after Tropicana. And today you're gonna talk about the response of tropical cyclone hazard to natural and forced sea surface temperature pattern.
Cool, thank you. Can everybody hear the word? Yes. Okay. Cool. Yes. Davide said I'll be talking about the response of TC hazard to naturally forced SST patterns, and this work is done in collaboration with all the authors here who kind of started this work and inspired me to start working on it. So I'm kind of writing with this. So just as a brief summary, and I know I wanted to give this a little overview because we're kind of moving to tropical cyclones. And I think we've learned a lot about how tropical cyclones respond to anthropogenic emissions or global warming. And essentially, we think that the hazard is going to increase with warming. And Tom Knudsen had a very nice review paper, two review papers in 2020. We think there's going to be increased total precipitation, rainfall rate, could be glossy clapeyron or super glossy clapeyron, higher average intensities, and also higher lifetime maximum intensities, worsening storm surge, which will exacerbate sea level rise. So these are all hazards. So we think that climate change is going to make tropical cyclones worse. And that's, I think, pretty clear from the research. So thanks for your time, and happy to take any questions. Of course, our understanding is going to be, is still evolving, of course, and it's not done. So I want to put this in context of the historical warming patterns. So this is showing you linear trends in SST, very simple in ERA 5 over the past 40 or so years. You can go further back, and it's not too sensitive to the time periods you use. And here I've taken away the zonal mean average, so it's easier to see the differences, zonal differences, and you can clearly see the East Pacific is warming less than the West Pacific. And there's this really striking pattern that looks very, very familiar to the canonical ENSO pattern. Here I'm just showing you the mode that explains the most variance in the tropics. And this is the ENSO mode. And so basically, if you flip the sign of this, which we call La Nina, it looks kind of like the observed SST trend. So we're calling this SST trend La Nina. Now, there's still arguments about whether or not the historical warming pattern is due to internal variability or whether it's forced. I think there's a lot of evidence now that it's actually forced trend and not just internal variability. So unfortunately, all of our models are struggling to reproduce this La Nina-like warming climate models, coupled climate models. Richard Seeger has done a ton of work at this at Columbia. So here I'm just showing the linear trend, the CMIP6 multi-model mean, and the large ensembles. And basically all of them show this, cannot reproduce this La Nina-like warming pattern, which we see in the observation. So this is a big problem in climate science. It's not just about tropical cyclones, it's about climate sensitivity and trying to estimate climate sensitivity and all kinds of feedbacks. That is important. But today I want to talk about how this is relevant to tropical cyclones and maybe start to get some of you thinking about this. So you might ask, well, why do we care about this? I think that's pretty clear from tons of research in more than it started many, many decades ago, that SST patterns, namely through natural variability, such as ENSO, are known to modulate many aspects of TC behavior. One of them, I stole this from Susanna's paper, I guess almost 20 years ago now, is that the ENSO strongly modulates the genesis potential or the genesis locations of tropical cyclones. So during boreal summer, you can see this northwestward to southeastward shift ENSO in the West Pacific Basin, and in the austral summer, you see this forward shift of these bands of the genesis potential during ENSO phases. So these SST patterns, which arise through natural variability, have been long been known to control tropical cyclone behavior. But SST patterns can arise via natural variability or climate change. There's no reason why SST patterns cannot arise via climate change. So just the motivation for this talk, we know that internal variability has patterns of ocean temperature, and the ocean temperature patterns strongly modulate tropical cyclone behavior. Now, a slightly less well agreed upon statement is that the world is warming, but non-uniformly. So I have an asterisk here because it's still under debate. And the question we want to answer is, we know that SST patterns through internal variability modulate TC behavior. And if the world warms in a non-uniform way, this might affect tropical cyclone behavior in the future. So just as a brief outline, I'm going to talk about the downscaling model that we use. I'm not talking about this today, but we've shown, we've done some work on the latitude of lifetime maximum intensity. I'm not going to talk more about it today, but just speak to me if you want to know more and how it's related to the pattern effect. And I'll finally talk about the tropical cyclone hazard and pattern warming. This paper is not even submitted yet, so I'm looking forward to your feedback. Okay, so of course, this downscaling method has been talked about before in this workshop, but we need to downscale climate models since a higher model resolution is necessary to sufficiently represent tropical cyclones in numerical models. You know, we're trying to connect climate timescales, variability on climate timescales, to phenomena that happen on daily weather timescales, and that's not easy to do. So we do this downscaling method, which was really pioneered by Carey 2 decades ago. Of course, these downscaling models were actually first started in the insurance industry, but Carey published it. So the model works by randomly seeding genesis points in space and time. You just evolve the track and intensity of the storm according to the large scale flow. The track evolves through a beta advection model, so you can just think that the storms are advected by the large scale winds. And the intensity evolves according to the fast intensity equations, which you can think of as just an approximation to a set of theoretical equations that you get from axisymmetric tropical cyclone theory. When you do this, actually, most of the storms die out, but you can just repeat this process many, many times to obtain a large number of synthetic storms. And this model is completely available online. You can go run it if you want. And a lot of people have been using it and giving me feedback, so that's. So this is just an example. This is actually an example of running this model on an existing storm like Hurricane Irma, but you can just get the general gist of how it works. So you have a genesis point. You have some track that evolves over time according to the large scale flow. And then you can evolve the intensity. I'm sorry, I used the Saffir-Simpson scale here, but that's the intensity of the storm. And you can even fit a wind model to it. So this is animation of the wind speed structure. I'm not going to talk about the wind field today, but this is an example of what it would look like. You can see you can decently represent asymmetric structure using simple parametric wind models. Okay, so what does the TC hazard look like? This is what I'm showing you is the return period of tropical cyclones that reach an intensity of 33 meters per second in the observation. So it's around category 1 strength. And on the top is the return period of these TCs. In the downscaling model, the middle is in the observations, and the bottom panel is the difference between the two. So there are clear biases in the model, but it does a decent job, especially in the specific for these storms. Okay, so we have this downscaling model that we think is a reasonable emulator of the real world. We want to try to understand how TC hazard and pattern warming are related. So the question we want to answer is, does tropical cyclone hazard depend on natural and forced patterns of SST? I think very clear that it depends on natural patterns from lots of research before, but it's not obvious if it would depend on patterns of SST, forced patterns. So the first thing we want to answer is, the first thing we're going to show is SST patterns owing to internal variability modify local TC hazard, and we're going to do this using ENSO as a classic example, but there are many other modes of variability that modify TC behavior. And the second is we're going to look and I'm going to hopefully show, maybe you'll be convinced that SST patterns owing to climate change also modify tropical cyclone hazard, and this is related to the observed warming pattern. So to do this, we're going to use the CSM2, NCAR's, the National Center for Atmospheric Research model. And it's a large ensemble project, which they ran 100 ensemble members under historical and future warming scenarios. So it's really, really large. I'm only going to use 10 of them because we don't really need 1,000. And we're first going to downscale the 1,000-year pre-industrial control simulation, which gives many, many iterations of many random combinations of internal variability. And to estimate tropical cyclone hazard, we're going to do something a little bit different. We're going to use the maximum wind speed, or just the intensity, of all storms that pass within 100 kilometers of a given point, and just use it as a measure of local wind hazard. And this was used by Carey and Jagger in 2010. So this is what example of the return period curve looks like. You can see a return period from the synthetic events in Carey's model in the blue lines, and the GEV theory in the red line. So it actually agrees quite well with the GEV theory. And the reason why we use this metric is because it's really easy to compare with observations. You just grab the intensity that from the best track data sets, and that's shown by the green curve. So this does a decent job, or Carey's model does a really great job, I would say, in representing, at least in agreement with the historical observed patterns of observed risk at New Orleans. But this is a really representation of local wind hazard. Okay, so what does our model look like? Today I'm focusing on the West Pacific. I'm just gonna pick Hong Kong as an example. So this is the model where I've downscaled in green, ERA 5, and in blue, just ignore the red line for now. The blue is the pre-industrial control downscaling, 1,000 years. So you can see the ERA 5 and PI control are in relatively good agreement about the hazard. The observations are in black, and the model is probably biased. The sampling at the 95% confidence intervals in the dashed green. But it does a decent job in representing the hazard. So, we are reasonably confident that we can use this model to understand future TC hazard. So the next thing we're going to do is separate the estimation of this TC hazard by the phase and magnitude of ENSO. So this is all in pre-industrial control. There's no force mix. And so this is what the hazard curve looks like during different phases of El Nino and different magnitudes. So during strong La Nina years, the hazard is greatly increased. You can see the return period of these storms at a fixed intensity. You can take 120 knots for instance, is much more frequent than during strong El Nino years. And you can see this modulation is really, really large. It's an order of magnitude in frequency. Now, the estimate of this is sensitive to the model behavior and the biases in the model. I've also done this on ERA 5, but it's a lot noisier because you only have 40 years. And the modulation is a bit smaller, but it's still there. So essentially what we've learned from this is that there's a strong modulation of local TC wind hazard by ENSO. Yeah. Sorry? I'm using the measure of the local wind hazard here, where I'm just taking the intensity of all storms that pass within 100 kilometers. No. But this is to easily compare with observations, because point-wise wind speed measurements are really bad. Okay, so what does this look like in space? I was just looking at a point. I'm showing you the return period of a storm with the intensity of the 1 in 100 year storm, but during different phases of El Nino. So you can essentially think that more than blue is that the hazard is decreasing, and blue is the hazard is decreasing, and red is the hazard is increasing. And so we see these really well-known properties of El Nino, where they shift the activity or the hazard in the basin northwestward during La Nina years and southeastward in the Western Pacific Basin during El Nino years. And it's really, really strong modulation of the hazard. The return period in strong La Nina years is very, very, of the 1 in 100 year storm is, 50 or 40 years. And I just want you to remember this pattern that we see on the top left for the strong El Nino or even the weak El Nino. Just remember what it looks like. Okay, so what about the SST patterns from warming? So what we're doing is taking the historical and future runs of the CSM2 large ensemble and taking the ensemble mean and just showing you the linear trend in SST. Very simple. And you can see here in this particular model, the East Pacific warms a lot more than the West Pacific. And we can quantify this by just subtracting the sea surface temperature from the box in East Pacific from the sea surface temperature in West Pacific. Very simple. This was done by Richard Seeger.
This one, yeah. Each scenario?
It's SST4. And this is, you could just plot this for the ensemble members and see what it looks like. the black line is, the red line is the ensemble mean, and the black line is a smooth version of the ensemble mean. So you can see there's this big trend towards this El Nino-like state where the East Pacific warms a lot more than the West Pacific. And this, we're calling this El Nino-like. And so we want to understand how this has an effect on TC hazard. So what we're going to do is downscale 10 ensemble members of the CSM2 historical and future runs and see what happens. So this is the red curve I told you ignore before, but now you can see the red curve, 2050 to 2100. I'm looking at the 2050 to 2100 hazard at Hong Kong. And you can see it doesn't really change that much from the PI control. Very strange. I mean, when I first saw this, I thought I was doing something wrong. There's small decrease in the hazard or no change at all. And this is in contradiction with a lot of research that has shown the hazard is actually increasing in time. So to try to understand this, we're going to isolate the changes not due to this El Nino-like warming by just conditioning on the East-West index. And that's a mouthful, so I'm going to just show you graphically what this looks like. So here's a distribution of this East-West index, a probability density distribution. Under black, the PI control, and 2000 to 2050 in the magenta, and green is the 2050 to 2100. So you can see this gradual shift in the probability density distribution towards El Nino-like states. And what I mean by conditioning on this East-West index is just to take a small range and just only look at years where the tropical cyclones are, where the East-West index is within this range. So when you do this, you can calculate the hazard curves. And what I'm showing in the solid line is the pre-industrial control hazard, and the dashed line is the 2050 to 2100. When the curve moves down, it means the hazard is increasing because storms of a particular intensity are getting more frequent. So the hazard is increasing at all return periods when you condition on this small range of East-West index. Now you can do this on any range you want. You can do this on this range, more the La Nina-like states. You get the same thing, the hazard increases. You can do this on El Nino-like states. You get the same thing, hazard increases. So no matter how you slice it, at a fixed East-West bin range, the hazard increases at all return periods. But this is strange because the total hazard, TC hazard, doesn't change, but the hazard at a fixed East-West index is changing, is increasing, no matter which part of the bin you take. So this is strange. So we're going to understand this by decomposing the total change in the intensity of the 1 in 100-year storm into just two components: the change that's not due to this El Nino-like trend and the change that is due to this El Nino-like trend. So these two will equal total change, assuming a linear decomposition. So the total change is easy to understand, and that this is the change from pre-industrial control to 2050 to 2100. And then you can just compute the total hazard curves. And that's what, this is the spatial pattern of what that looks like. So you can see in like if you just look at Hong Kong, the hazard doesn't change all that much, and it doesn't change all that much across most of coastal Asia. Yeah. Yes. Look at the intensity of all storms that pass within that grid point, and then do that for many, many, many years, and you can get the return. You can estimate the return period of a storm of a particular intensity. So this is essentially saying, this is a lot like related to a lot of attribution work, right? If the 1 in 100-year storm is 100 knots and it increases to 105 knots, you can say climate change is 5%. But here we're saying that climate change is not making any change at all. So we can estimate what the change is not due to the El Nino-like trend by taking the estimates of the hazard by fixing along this small range of the East-West index. And this is what you get in the middle panel. Hazard increases everywhere. And this is what we saw earlier when I was focusing on Hong Kong. And so you can just subtract the middle panel from the top panel due to this decomposition, and you get the bottom panel, which is the change due to the El Nino-like trend. And it's negative across all of coastal Asia. And it looks like that pattern that I told you to remember. It looks like that pattern before. And that's actually by construction, because we're trying to isolate the effect of this El Nino-like trend. So what this is saying is that in a world with no El Nino-like trend, the TC hazard increases everywhere, nearly everywhere. And this is we think this is primarily due to the potential intensity effect. Potential intensity goes up with greenhouse gas emissions, and it goes up everywhere. But the shift towards this El Nino-like state actually cancels out the overall warming-induced increase in TC hazard. And we have this evidence here that it's doing that. And it's, by canceling out, it's important to note that it's the same order of magnitude as the change in the same order of magnitude effect as the greenhouse gas emission forced in the means. So the pattern of warming with climate change is modeled to be El Nino-like, but our observations are actually showing a La Nina-like trend. So you can ask a simple question: what happens if the La Nina-like trend continues? And Jing Yi, who is going to be here in a couple of weeks, has been doing a lot of work on this in an actual climate model. I'm kind of being lazy and doing it in a worse way, but we're going to just try the storyline approach where we assume a La Nina-like trend. The La Nina-like trend, where two scenarios: it stops in 2020 and stays the same, or it continues through 2060. And this is just a graphical image of this. So you can see this east-west index over time. The blue line is the 10 ensemble member average, where you can see it's trending towards this El Nino-like state, positive values of the east-west index. Whereas had ISST, it's an observational SST data set, you can see this trend towards the La Nina-like state. And so all I'm doing is fitting a line to the observations from 1960, and just assuming it continues in time or it just stays the same. So we want to estimate what near-term TC hazard might look like. So you can do this, and this is what the return period of the 1 in 100-year storm during pre-industrial control conditions looks like. So essentially, if the return period is greater than 100 years, that means it's increased hazard. The hazard is increasing. And so the top panel is kind of the more conservative one, where we just assume that the trend doesn't continue and it stops. And you can see the 1 in 100-year storm is actually increasing in frequency to every 25 to 50 years. And you can view this estimate as something that has already happened. The 1 in 100-year storm during pre-industrial control has already changed in frequency to every 25 to 50 years, because we're just assuming that the trend has stopped. And you might think this is it's a very kludgy estimate of the hazard, but the hazard has increased because of the La Nina. So this is a little bit concerning if you are worried about TC hazards. So this is something I wanted to talk about because I think this is very important. What I'm showing you again is this east-west index trend in the ensemble members, but now I've overlaid in magenta the tropical average warming. You can see in this model scenario, the tropical average warming at the end of the century is more than 4 degrees. It's huge. It's much, much larger than the magnitude of this mismatch in warmth, which is around only a degree and a half. But we saw in the previous few slides that this 1.5 degree change in regional SST patterns has the same effect on TC hazard as 4 degrees of tropical average. That's quite interesting to think about. And I think we actually know why this is the case. Local SST changes are much more effective at changing potential intensity and other tropical related variables than our global SST changes. This was work done by Carey and Adam in 2013. And this is basically due to the large deformation radius in the tropics. If you want to know more about it, you can ask me. But this is why regional SST patterns have such a strong control on tropical cycling behavior. And even if the regional patterns are not the same order of magnitude as the global warming, the mean global warming, it still can have a really big effect. And so the take-home message today that I want, the single take-home message that I want you guys to take away from today is that warming patterns, and not just warming magnitude, are leading order contributors to future TC hazard changes. I think there's theoretical evidence for this, and we are just starting to do some modeling on this. So I hope that people are working on attribution, storylines, all these other methods I hope they start thinking about these warming patterns and not just warming magnitude. So just a summary, climate change is expected to increase TC hazard, but the change in hazard is very sensitive to the exact warming pattern and not just the warming magnitude. And therefore, forced SST patterns are going to be a leading source of uncertainty in how future TC hazard will change. But it's not easy to constrain regional SST patterns as it is to constrain global warming. Lots of people have been working on climate sensitivity, but how do you constrain how regional SST patterns will change? It's not easy. And of course, there's this discrepancy between the models and observations in the Pacific SST warming pattern. And this is a huge issue right now if you want to project TC hazard in the future. And, of course, you could pick at what I've done. We only used one climate model, one emission scenario, one downscaling model, right? We didn't want to do a whole modeling intercomparison, but just try to show a proof of concept. And really here, we're focusing on the ensemble members of the model because you want to try to get the internal variability too. And as we know, there's actually a wide variety of model responses to the same forcing. You can see this in the CMIP 6. So something to try in the future would be to use a variety of models to have a variety of by model responses, I mean patterns of warming. There are different patterns of warming for the same forcing. But what's important to note is that nearly all the models have an El Nino-like response at the end of the 21st century. So if the models are right, it might be good for TC hazard that's canceling out this warming, the global warming induced increase in TC hazard in the future. And so I wanted to end by a few discussion points, and maybe we can expand upon this after, but just to say, why should you care about this? I know there's a variety of people, scientists in this room work on different aspects of the same problem. So I want to put this all into context of Tropicana. So for those who work on high resolution modeling, it's common to do the storyline approaches where you put some amount of warming into your model and say, look at the impacts of how tropical cyclones will change in the future. But I think this work has showed that it's not just about the magnitude of warming, it's also about the pattern of warming. And it's much harder to do that in a climate model. So how do we define good storylines that incorporate uncertainties in the large scale SST patterns? I think this is going to be very crucial. It's not just about increasing the temperature in the model itself. The second is attribution. Warming can project onto modes of internal variability, but the fluctuations in the modes are not natural, they're forced, right? So when you want to do attribution, you want to get the climate change signal, but it's not easy to decompose fluctuations in a mode of variability to the parts that are natural and the parts that are forced. So maybe there's some, people who work on attribution start thinking about how to do this. And the final is adaptation. And I think this part is the thing that worries me the most. Lots of adaptation. So lots of cities, municipalities are thinking about adaptation now. Climate adaptation is a local effort. And what they want to know is, for instance, what will this particular hurricane that happened in the past look like in 2100? And we are giving them answers. This is what it's going to look like. But that's informing about the mean change. They really need to know about the full uncertainty range in the local TC hazard change. And my hunch is that the full uncertainty range, because of this pattern effect, we don't really have a good idea of how it will evolve in the future. The uncertainty range of how TC hazard will evolve in the future is really large. And I think it's going to swamp out the mean warming signal that we get from just global warming. So it's a little bit, I appreciate any thoughts on this. Maybe you have comments on the work I've done, but thanks for your time.
Thank you, Jonathan. Yes, I see already many hands.
So thank you. I really enjoyed this, and I think this is really important. I don't know if you can be here for the discussion on high-res MIP when Malcolm is around, but there are sort of two camps now in high-res MIP. One is obsessed with realism, and the other one is proposing we do things like this, where we try to understand and not go for scenario 8.1.2 and scenario 8.1.2.1.
Sounds like you're in the former camp.
Yeah. I think so. So Kevin Reed is now part of high-res MIP, and this idea that we need to have very idealized setups and imposing patterns in one of we know about this error. There is a huge hope that the eddy-rich models might fix this, but that's a wild hope. In the meantime, this can help us understand really what the hazards could be. So please, the people who are here, unfortunately, cannot be here. But please argue for it. This is a big deal. This is really important, and we should do that instead of obsessing over what scenario it is. The only other thing I wanted to ask, so at the start you had a map that showed what the error in return period is, and it seems to me on the rims of the distribution of tropical cyclones, you have quite a large error, up to 50 years. You said, oh, it's doing a good job, but on the rims, it's not. Probably where there are very few, the error is large. Could you not use that information to mask out your, yeah, on the rims of the distribution, you have quite a, should you not try to use this to mask out where your projections are more trustworthy and where we should be a bit cautious?
Well, I should know that. On the rims of the current period category one, so it might be for 25 years,
Yeah. But should you know, because you could have a sort of stippling or something on your projections so that we really focus on the big signals and what, so because when we assess the models, it's important we really see what we're aiming for.
Yeah, that's all I think.
Yeah.
So CESM has a fairly significant double ITCZ problem, as most of these models do. And in fact, Pierre Luigi, you should know that it sets up even in an AMIP simulation where the observed SST is correct. And so how credible is a future El Nino-like state when the models can't simulate the observed SST pattern very well at all?
I mean, that's a great point. We're not I think, I'm not a climate scientist and a climate scientist. I can't say what exactly it would be. I think what I'm saying is that certainty range, whether or not it's medial line.
And to follow up, do any of the large ensemble members, does any single realization project La Nina futures?
Very
This is the first time. Well, I just want to say that, well, so there are some model, yeah, it's a small number, and their La Nina-like pattern is not as strong as observed one. So I don't have a list right now, but there are some of them, at least 18 or 20 of them can be classified as La Nina-like pattern in the CMAP models. And I think our student who won't be here, but also show this is model seems doing slightly better with high-res MIP compared to their low-resolution version, but not yet to be totally turn over the pattern. And next week when Jingyi will be here, that she will show that fixing the ocean can helping the model to fix kind of a warming El Nino-like pattern, but not all the way to the end of 21st century. And partially it's because there are some, just like you say, even when the model, the SST is correct, there's still a double ITCG bias. So it's not only ocean, maybe some view of atmosphere. Yeah, many parts of causing that.
Just say something. We have a scheduled discussion for next week about uncertainties and projections, and Jingyi and Liz Ritchie are going to lead that discussion.
Thanks, Jonathan. Quickly, yes. So you mentioned some of the theory and potential intensity and things like that. So I guess my question is, have you or other people looked at a kind of an interim analysis where you've done this same sort of thing, but looking at how it affects potential intensity?
Well,
no, but in
single column simulation.
Yeah.
Do this by putting the WT parameterization.
Which I've done with Adam years ago, but in terms of this pattern effect, anyway, not so much an idealized, but more like what you're doing with the large ensembles.
No, I don't think so. I mean, I think the thing that is hard to do in a final model. Frequency and magnitude and so.
Yeah.
And ideally, you would look to do like the full-on understanding of how the event properly cycle variables. You want to be able to do it. I think Lexi better off did an experiment where they put a permanent El Nino, a permanent La Nina, and essentially what happened with that destroys the PC relationship that so because we no longer have this mismatch in the long dimension. So I think I'd like to see more of these idealized studies on and so the physical mechanisms and behavior because it might be important there. But it's just really hard to do.
Yeah, cool. Thank you.
Here, but we will resume it. Thank you very much, Jonathan. Yeah, for this kind of problems, my personal feeling that we have already the methods to go with, but the data and the models we struggle a little bit. So that's I think it's an interesting. It's important to go to idealized models, otherwise we're not gonna get through. And yeah, it's now we go up in the sky from the ocean to the sky, and let's try to fly inside these changes of atmospheric circulation patterns, and let's see how turbulence will change. So if we can make sort of attribution of turbulence, and it's a great pleasure to introduce Tommaso Alberti, who is a very active member of Climameter also, besides being a good friend of mine and also a great researcher at the INGV in Italy. And so I let you explain what we are doing with the turbulence. Thanks, Tommaso.
So, good morning, everybody. Thanks, David, for the introduction. Yes, we come back again on something that is related to the attribution that most of you saw yesterday in the framework of Climameter, and the methodology is not to say. But we are looking on a different type of impact because yesterday we focused on precipitation, wind speed, and temperature by looking at the SST variability. Now we focus on something that is related to the velocity speed, but which is known heavy dissipation rate of turbulence. So we jump at level 200 hectopascal level to see what happens. And this is a joint work with David, Elia, Erika, Fabio, manager here, and the main purpose, I think you. Okay, I will start with some very recent and active part because maybe all of you know about the recent project experience. Singapore Airlines in terms of turbulence, there was a mediatic effect on the role of climate change affecting a specific kind of turbulence that you will see in my presentation, but that's not the main sources of this episode because it has been quite well understood that it was not some kind of clear turbulence that I will describe later, but it was something related to the fast evolution of a thunderstorm that was behind the flight level. But it was a mediatic effect on infrared journal. You can see here newspaper from Italy, France, England, yeah, Japan. And indeed, it was also a mediatic effect, especially on Italy, which is not so usual because in my personal experience, Italy is, I would say, not so much close to what happens in climate change. So it was interesting also to make some kind of interview explaining that there are a lot of effects of climate change on turbulence. And so I will start with some very few words on turbulence because I see that here we have very heterogeneous. So maybe you can know about turbulence that is a really unsolved problem. This is an unusual sentence that you can don't have a review or book on turbulence. And then back to Leonardo, who has drawn some interesting pictures of water falling from a source that you can see here. that you can see here. And then you see that when the water falls, you can see a lot of formation of vortices of different sizes. And that tends to dissipate into smaller and smaller ones. And then it has been proven by Reynolds in 1883 that there is some kind of parameter that controls the development of turbulence. And it is the famous Reynolds number, because he noted that when there is a particular combination of the speed of the flow, of the length, of the characteristic size of the experiments, and the viscosity, so the chemical composition of the flow, you can have the development of turbulence. So when you have a laminar flow, this is typically related to lower Reynolds number. When you increase this number, you can see that in the channel, there are the formation of different vortices. And this, the formation of different vortices, led to Richardson 1 century ago to develop the first idea on how to explain turbulence in terms of injected energy at large scales, like you can see here from the Leonardo picture. And then this is suddenly dissipated through vortices of different sizes. And you can see the formation of vortices of large scale, small scale, and then there is a lot of theory on how this behaves together, and you can form from small scale, larger scale, and the opposite direction. So just why Richardson and why we need for turbulence, because all fluids like the atmosphere and the ocean have typically large Reynolds numbers, and only at a small scale, so this is also a problem of resolution, these fluids are able to dissipate the excess of energy that is injected at large scale. So if you assume instead of the, in the context of climate change, if you inject a lot of energy into the system, this needs to dissipate over longer time, but to dissipate, you have to reach smaller scale. So this is a problem of converging different types of scale. And the main idea of Richardson was the cascade. So if you have large vortices that typically break out into smaller and smaller ones. And the idea was correct for two different reasons. Why? The first one is because there is the Reynolds number that controls the behavior. And the second one is because when we look at the equations, which are the Navier-Stokes equation that you always know in terms of the description of fluids, there are two important terms. The nonlinear one, which is responsible for developing this breaking of the vortices, and the dissipative term, which is responsible for dissipating this vortices. And interesting, when you make the ratio of these two, you recover the Reynolds number. So the Reynolds number is not an experimental quantity only, but it's connected with the physics of the problem. And another important thing is that the idea of Richardson that you have one large axis that breaks up into smaller and smaller one is right, also because the Navier-Stokes equation are scaling invariant. So if you make scaling transformation, you can see that the equation remain the same. And this is like a matryoshka. So you can describe that you inject the energy at the large scale with a large scale vortices here, and then you develop the so-called inertial range, so where energy is transferred from the large to the smaller scale. And in the meanwhile, you have to think that these vortices are breakups into smaller and smaller one until you reach Kolmogorov scale, so the dissipative scale, where you have the primary role of the viscosity to dissipate the energy. And there are almost two theories. The first one, the theory to explain the Richardson cascade are based on two hypotheses. The first one is that you can describe vortices with field increments, so difference of the velocity field typically. And the second one is that the process is stationary. Then the first idea was proposed by Kolmogorov, so assuming that you have a scale size L that is broken out into two different vortices of the same size that are then broken out into two vortices of the same size and so forth. This means that you preserve an interesting quantity, which is the amount of the energy transfer rate, so the amount of energy that is moved from the large to the small one. Then it has been proven by several experiments that this is not the correct description. And this has been refined in 1985 by Maurice and Frisch, who proposed that the vortices that you form are of different sizes. You can explain with some kind of rules that you can define this particular P1 and then the successive one. But the main idea is that you have irregular structures at different scales. And the main problem is that in this case, you do not preserve the energy transfer. And this is important because this means that you have to look at the different scales, and in particular at the smallest one, to fully understand the turbulent problem. And what is interesting is that this quantity is related to what we use in turbulence to characterize the level of aircraft turbulence, which is the eddy dissipation rate. Is exactly this energy elevated to the power 103. So if you are interested of more and more review on the problem of turbulence, there are interesting books by Frisch and also Bruno Carbone, and also interesting review with perspective by Berenger in 2019. So these are some examples of real-world turbulence. I prefer the first one, which is on the upper left, because you have turbulence when you put pasta. But there are a lot of examples of turbulence because you have this, the mechanical turbulence, which is close to what Leonardo was drawing, because you have typically an obstacle here that interrupts the propagation of the fluid, and then you have that typically you form some kind of small scale structures. You have the wave turbulence, which is also experienced by aircraft, and you can see here when you have two different, for example, fluid motion that interact with each other. And the other one, which is really, really interesting, is this one, which is a video taken by the Goethe, not Goethe, but the Meteosat over the Canary Island. And this is not a simulation, but this is real-world observation. You can see that there is here Gran Canaria, and then when the atmosphere and the air masses fall close to this island, you can see the formation not only of small-scale vortices, but also large-scale one. And this is a particular turbulence, which can be also described by experiments like those conducted by Berenger in terms of rotating fluids. So this is an interesting application. Concerning the aircraft turbulence, they are almost the same because you have some kind of convective or thermal turbulence because you have a gradient of temperature between the surface and the level when we are flying. And typically, if you fly over the cloud, you have a smooth flight. When you are close to an airport, typically you experience more turbulence. And this is mostly related to convective turbulence or thermal turbulence, so gradient of temperature. Another one is, of course, when you encounter some kind of structure like thunderstorm, which is mostly related to the irregularity of the thunderstorm. Then you have wave turbulence, which is related to the fact that you are flying on same lines, on same flying level by the aircraft, or when you are on ground. Typically, when you take off, you can see that there is some kind of distance of security between one aircraft that leaves out and then when you leave. And this is related to the fact that you create some kind of very large wave turbulence behind you. But the most interesting one, also in terms of climate change, is clear air turbulence, which means that you have turbulence without any advice. So this means that you have clear sky, you have no such kind of thermal gradient that can happen in that region, and which is mostly related to the fact that you have velocity shear. So if you have some kind of differences in the velocity, basically the vertical one of the air masses of the atmosphere, but you cannot see really what happens. So I don't know if you have wondered how your flag will be importable or not. There is an interesting application which is Turbly, and this is the result from my yesterday flight from Rome to Paris. And what is interesting is that you can see the measure is what I introduced before. So here the dissipation rate. So you have to focus on this one, and depending on the value assumed by this eddy dissipation rate, you can classify the turbulence into different categories, typically light, moderate, and strong. And my flight was really light turbulence. So I enjoyed it. Yeah, yeah. You can go on Turbulence Susanna. You can ride your airport starting and then airport. Choose your flight because this is optimized for the specific flight. And you can have the prediction of turbulence. You can see the wind map, also the chance for an early arrival, how will be your takeoff or landing. So, and only based on this quantity, which is mostly the basis of turbulence, but can be for applicative reason or different. Here one, they are classified into categories, but when you make this one is in middle to the 2/3 and second to the by one. So up to the 1/3. Yeah. It is scaled because this is mostly related to the fact that Kolmogorov proposed that there is a global scale invariance with an exponent which is 1/3. So this can be connected to the length or to the size of what we expect. And there is some evidence indeed that the climate change is increasing the possibility of experiencing especially clear air turbulence. That was Paul Williams with now and previously worked on turbulence. The first paper was this one, and I think this is interesting for Susanna because he focused on flights, for example, from London to New York City, and he made a lot of work in terms of how climate change is changing the travel time and also the conditions. And you can see that he used a lot of indicators, sometimes more or less also connected to each other. But you can see that for every class of turbulence that you can see here, all these indicators suggest that there is an increase of their numbers of the values. And this means that there is an increase of turbulence. And depending on the class, this is not linear. And so it is more likely also to observe some kind of moderate up to severe level of turbulence. And the first category that has been impacted by the increase of the climate change is the clear air turbulence. So when looking over the past 40 years, they found an increase of the 55% of the chance to be involved in some kind of clear air. So what we do is to use the climameter approach because the previous studies were based on fitting linear trends on the dissipation rate or some kind of indices. So you have your map of your indices, and then you, for each box, make a linear extrapolation over your time interval. And you can see this is increasing or not. But this is not exactly connected to the source. So what we do is to define a region of interest. In our case, it was the Europe, also because there is no literature on Europe. And we use the ERA 5 data. We define to search for pattern as you understood yesterday, the sea level pressure in this case. And we use the Euclidean distances. So the distance between two different patterns, as we explained with Davide yesterday in the climameter framework. Then we divide the full interval into sub-intervals, and we count the number of analogs typically every decade to see if there is an increase of the number or a decrease of the number. And we estimate this trend not on the grid size, but on the number, so on the frequency of occurrence of specific events. And if we have the linear fit as a positive within the error bar coefficient, then we say that, okay, this is an increasing trend. If we have that it is negative within the error bar, this is a decreasing trend. Of course, we can have also some kind of neutral trend. And the difference with climameter was that instead of focusing on precipitation, temperature, and wind, here we are focusing on the eddy dissipation time at the flying level. So we see directly as an impact variable what is experienced by an end. So the novelty is that now the trends are extrapolated on patterns, so we use analogs and non-linear extrapolation of the maps. And then we have the pattern of the surface of sea level pressure that impacts on the eddy dissipation rate. Okay, this is in terms of what we call for the circulation anomalies. And you can see that increasingly frequency anomalies are mostly characterized by more cyclonic conditions over Northern Europe and more anticyclonic conditions over Southern Europe, while there are decreasing frequency patterns that are mostly associated with anticyclonic conditions over the North Atlantic and cyclonic conditions over Scandinavia. There is a clear sign of seasonality that you also see yesterday, for example, in the clinometer. You can see that the most frequent encountered pattern now mainly occurred in January, February, and December, with a decrease, especially during summer months for European countries, while what they are disappearing mainly previously occurring on May, June, so in summer. So, although there is no clear seasonality in terms of the less frequently encountered pattern. And David also worked on the impacts on temperature and other meteorological variables, and they were associated with windy, warm, and wet conditions over North. So when we look at the eddy dissipation rates in terms of the anomaly, you can see that the most turbulent conditions for increasing frequency are now recovered over the UK and the Scandinavian region, which are also related to the cyclonic conditions that we found for the SST pattern. While when we have a decrease of the eddy dissipation rate, we have mostly anticyclonic conditions. The interesting thing is that here I saturated the color scale between -0.1 and 0.1. But you have to consider that to jump from moderate to severe, the difference is between 0.05 and 0.1. So this means that having an increase of 0.05 or 0.1 brings you to another class of turbulence. So from light to moderate, for example, or from moderate to severe. While when we focus on the decreasing frequency, we can see that there are smaller values of the anomaly of the eddy dissipation rate. So this suggests typically on average and over the domain less turbulence conditions that are disappearing now. And then you have that there is no clear association between the cyclonic and anticyclonic condition and the increase of the eddy dissipation rate. So we make a further analysis to see which are the weather patterns that can be responsible for this one. And what we found is that the mainly cyclonic conditions, which are also associated with increasing turbulence, are related to trough. One, there is an interesting region which is covered by ridges when we have anticyclonic conditions. So this means that we have more of these anomalies related to mesoscale structure over Central Europe. And what is interesting, but later I can show better, there is also an increase here for what could be related to the role of the jet stream, especially the subtropical jet stream. While conversely, which patterns are disappearing in terms of frequency are related to trough associated with cyclonic conditions or ridges which are associated with anticyclonic. So we have two categories that can clearly distinguish between the two. And another thing that we also do is in terms of divergence anomalies. This is especially important when you fly over mountains. And you can see indeed that there are a lot of mesoscale structures over the Scandinavian regions, but also the small scale structures over the Alps, the Pyrenees, and also some kind of mountain waves over Portugal. And you can see that there is a difference with what happens for increasing eddy dissipation rate over the UK, because these are large scale patterns. And when you fly over the mountain, this is typically related that you fly over clear conditions or stormy time conditions, while when you approach mountains, you have small scale structures. While for the decreasing, we have not clear pattern for the in terms of the divergence. And when we make the statistics of the different classes, we can see that the increasing in terms of frequency, we can see that there are a lot of episodes of moderate or moderate to severe or severe features. And most of these are typically associated with converging or diverging range. Oh, this means clear rectangle. And also some experience in terms of stormy time condition. While they are completely disappearing, this moderate or moderate to severe class of turbulence. So we are going to experience more moderate and severe episodes of turbulence with respect to the past. And you can see that there is an imbalance indeed. There is a lot of disappearing in terms of light turbulence, which is now traduced into moderate turbulence. So this means that there is a shift related to climate change. And when we focus exactly on only on moderate or severe regions, we have the mostly 30 to 40% of encountered moderate to severe turbulence over the North Atlantic, which is in agreement with previous work, but also over the UK and the Scandinavian region. And this is mainly related to region. When we focus on troughs instead, we can see that there is a lot of contribution to the Southern Mediterranean that we now are attributing mainly to the subtropical jet stream, but this is a future work that we are intended to investigate. Also some kind of the North Atlantic jet stream. And what is interesting is that this is not the best color scale, but here there is an increase of the Alps and also over the Pyrenees of about 20% of having moderate or greater episodes of turbulence. As a last example, you understand yesterday that climameter works for single events. So David introduced yesterday the depression Daniel. You worked on the American Llanos, so there are a lot of strong impacts on the Greece, Libya, and with precipitation, and also with a lot of winds, also making some kind of damages in terms of civilian infrastructure, but also airport closure. And so when I tried to make the same climameter, but using the energy dissipation rate as an impact variable, and not the precipitation of the wind, you can see that typically the past analogs, so similar events to Daniel in the past, are typically characterized by low level of the energy dissipation rate. There is some kind of increase where the core of the depression was located, and something on the North Atlantic, which is related to the mainly to the jet stream. When we see at the present analog, so in our present pattern, you can see that events that are similar to Daniel blow now moderate to severe turbulence over an extended region of the Northern Europe, but especially over the region where this type of events mainly decide. So you have not to take care only of long-term trend, but also on specific events. And when we make the difference between the past and the present, you can see that there is an increase of turbulence over France, over Western Mediterraneans, over Southern Mediterraneans, and also over the Balkans and the eastern part of the Ukraine. And this is mainly related with what you found yesterday in terms of the velocity. But now this is at the 200 flight limit. So the idea could be, if David agree, that we can run some kind of turbometer instead of climameter, and we can make something that can be useful not only for flight level, like the turbo, but also in terms of the ground effects, because there are a lot of works also on the restriction of takeoff distances, weight requirements for your flight, because if you have different conditions on air, you can have different weight. So concluding, the main results are related to the fact that shifting atmospheric circulation patterns led to anomalies, more anomalous conditions in terms of turbulence, especially over the UK, the Northern Europe, but also the Southern Mediterranean regions. This is mostly associated with moderate to severe episodes, and they are mostly associated with clear air turbulence, so clear sky. But when we look at specific events, we can see that, of course, this event is important for leading increasing turbulence condition. And this is a complementary approach with respect to the usual trend estimation on the data set. So as a suggestion for Tropicana and as a to-do list, we are working now on attribution of single events. There is Leah Rapella is working now on different events and different sorts. But concerning the modeling, for example, it is important that we go towards higher and higher resolution because turbulence you see at the smaller scale. So if you increase your resolution in terms of observations and models, you can really see the different paths in terms of turbulence and follow a specific flight, for example. So we need high resolution outcomes and also interdisciplinary expertise. So we need something that can join in terms of satellite, weather regime, also in terms of weather conditions, modeling, future projections, and so on. We are working with Erica on using regional climate models for Europe to see in the future what happens, and also to jump into the possibility of making some kind of aviation sustainability in terms of making greener our flight. There is mainly a long list of things that we can discuss in the afternoon if you like. And I thank you for your attention. I just bring you that there is an open PhD position in Italy, working on turbulence and climate change in the Mediterranean region, focusing on extreme weather events and mitigants. So if you are interested or some of your colleagues can be interested, please share the voice. And thank you for your attention.
Thank you, Tommaso. Yes, some experience of flying in the Medicans by my friend because since the forecast sometimes is not also very good, so they just fly.
Yeah, regarding turbulence measurement, are you aware that there is a way to measure turbulence rate via, you know, when there is a cloud and there are some ice plates in it, the orientation, the way they, when they fall, they do like this, and this depends on the turbulent level. And 20 years ago, I published a paper where we correlate this with turbulence. So these are satellite data. This is I mean, at the time it was done with polarized data, but maybe there are still some satellite like this. And you should couple with this because this is a direct measurement of turbulence rate. That does not rely on you know, on small scale or downscaling or whatever.
Previous works when there were some flight specifically flying within hurricanes or that. And there is, I think, also an international effort, Pianos, there have some kind of data, not for all flight, but there are some flight that measure wind, temperature, yes. Yeah, I remember some papers by short. But I don't imagine. Yeah. Thanks. Okay.
Yeah, so thanks for the very interesting and entertaining talk. The very personal comment. It's not scientific. From a scientific point of view, it's very interesting what you are discussing. From a personal point of view, I consider aircraft activities a threat to climate rather than the other way around. But so it feels like the climate is fighting back. Anyway, okay, I have a very precise question. Is you use this de-dissipation rate? So do you take them from ERA 5 and can you trust them from the model?
I evaluate this one by using the wind speed data of the ERA 5 one with the micro. 200 Pascal, so we have the wind speed data and then we evaluate the difference at the smaller scale, which is the yes, there is a strong evidence that it is quite robust in terms of the evaluation. Also compared over similar flight when you measure that in the front line.
Okay, so that's what you were discussing, that they are some measurement. Okay.
There is a paper where they compare the dissipation rate measured by year and time and comparison of what has been measured in flight. Yeah, and there is actually turbulence somewhere really measurements on flights, documents are flights, and runs in the company that gives you data and modifies in so if you have 2 funny things to spend, this will be great.
Cool, thank you.
Then before.
Yeah, I was curious, like a very general question about what processes induce clear air turbulence. And you were showing like the troughs correspond to like more turbulent areas. So how does that happen?
The first question is, so if you're needing, okay, it's not, yeah. Typically, it has been attributed to velocity shield, so vertical or velocity and apart from constant, the difference between these two. And in this, when you experience turbulence, you can kind of always change the other. So you can get perspective of the path, but this is where it is all but you know, evidence is after that. Didn't be like this one and we that that's what the one and it's the delay everywhere we want to do by the second part the map, yeah. The difference is that the great majority of that is moderate is the direction. But in those then we have the north to the so the problem is that graphs represent more percentage with respect to the participation. But when we look at the different graphs, we have they were okay in another part of the Tropicana because they fly over thickness from we are like the 7,000 feet in not experience anything and then it was having to do something. So this
Yes, my question is related, I think, to these first two questions. It's about what is the typical size of the eddies that produce the turbulence? Because naively, I mean, the frequency is about a second, or the period is about a second. So the typical size of the eddies that is associated would be 100 meters or so. And so you've spoken about high resolution. So do you mean that resolution when you mean high resolution? And second, when you describe the method you use to evaluate the dissipation rate by subtracting the velocities at 2 different time steps in AR5, that's way different from a fluctuation at a second frequency.
One, yes, it wouldn't be the deal what would happen. Really, I had to show measurement because we can so something like seconds or because it would be that. But concerning this is now possible for students like so yes, kind of measurement for five family time. And the second one, yes, indeed I was fully advised to work like all the meeting. But now he evaluated the because of going to have some kind of 0.5, 0.25 degree of reduction in the gap for less than and 1 hour to do. So I make some kind of testing kind of way to differences in space and time of course, at that regime, there is not so significant difference. So if you evaluate the step between a difference of 1 hour, and if you evaluate the gradual function gain, this means of the resolution. Of course, this is not the natural range of turbulence because we are outside, but this is a proxy of what of the energy junction.
But not only the scale are very different, but also the processes that produce these fluctuations in the model, they are completely different from clear air turbulence.
Yeah, indeed. Indeed, we are working also with ERIGA, which is working on model resolution, and so 1 kilometer with and we see, of course, that there is some kind of thing place, but the result that we obtain, for example, over the Alps and the Pyrenees, is mostly related to the fact that sometimes you can associate this one with clear air turbulence, but this is not clear air turbulence. This is a reflection of the point scale structure that you cannot resolve in terms of phenotype. So yes, of course, this is a proxy.
If I can add,
also purely for turbulence and can compete. This is not exactly the vector rate because there could be another way. For example, if you look at the cross sterility between the component of the velocity field that gives you a more total way to the traffic time. But yes,
yeah, another thing is like in the Medigain example, we don't see the Medigain basically in the analogs. So that means that basically we are capturing the turbulence, the change in turbulence linked to the jet, but not absolutely nothing related to the Medigain. That means that if we want to have like a turbometer that takes into account also convection, then we need convective scales. Otherwise, we are not all perhaps the convective scale, but we have it to be in the convective regime to then extrapolate.
Yeah, which is the closer one to the resolution of the file.
Yeah.
Before jumping into the model.
Yeah, exactly. Yeah, so that's really
there
something
are
interesting to look in your data.
Yeah.
Yeah.
Yeah, this is
The LES of Florian. Yeah, we have to close, but then we can continue the discussion with Tommaso, Beranger, and with interested. Thanks a lot, Tommaso. Yeah, and Florian, I agree with you that planes are bad for climate change, but they will still fly. So if we can make them save some CO2 emissions while they make their routing. Yeah, exactly. Yeah, that's the idea is that they stay less in the air if we can give better routing. Open discussion as well.
Yeah. Yes, of course.
Io ho una riunione ora, ma ti lascio. But even if that's wait for me.